Hello, George Romanic here. Welcome to Fundamentals of Weather and Climate. In today's video we are going to talk about daytime heating. Why is daytime warmer than nighttime? Of course, it's because we have sunshine during the daytime. But let's be more technical and examine this in more detail so you properly understand what is actually contributing to high temperatures during daytime. Which physical processes govern daytime temperature? We will examine this question from 3 points of view. First, we will look at the position of the sun in the sky and how that contributes to heating of the surface. Then we will look into radiation balance, and thirdly, we will look into energy balance at the surface. So please make sure you familiarize with the videos on radiation and energy budgets from chapter 2 of this playlist, and please familiarize yourself with the video on the position of the sun or angle of the sun in the sky from chapter 3 of this playlist. Now let's start. We start by considering Earth's surface in two different situations. In situation number 1, the sun angle is low in the sky. Sun is indicated with the S, and therefore sun rays have this low angle, let's call it alpha, with respect to the Earth's surface. In situation number 2, sun is high in the sky, which corresponds to hours around local noon. So you can see that the sun rays have much larger angle, alpha, with respect to the horizontal surface than in the case when we had morning hours. Now, from my video on the intensity of solar radiation, you know that these two rays will be distributed across much larger surface area compared to two rays here that are concentrated over much smaller area. And that means that the warming of the surface around local noon hours will be much more profound than the warming of the surface during the morning hours. In addition, during the morning hours, the path of sun rays through the atmosphere is much longer, so there is more chance of these sun rays being backscattered into the outer space or being absorbed in higher regions of the atmosphere, thereby not reaching the surface of the Earth. Now, again, from my previous videos, we know that the atmosphere is predominantly heated from underlying surface. Namely, these sun rays heat the Earth's surface, and then surface in turn is heating the atmosphere. And that heating goes through the conduction first. Remember, we discussed conduction and convection. Conduction is the dominant and the only mechanism that transfers heat from the surface through the adjacent layers of the atmosphere to the surface. But you will kindly remember that this conduction of heat is only important in the first few millimeters to first few centimeters above the Earth's surface. And this flux of heat through conduction is here indicated with this wiggly arrow. But because surface is warmer here at noon hour than at the morning hour, this flux will be higher around noon, so I can indicate it maybe with 2 arrows. Because we know the flux depends on the temperature difference between the atmosphere and the surface. And the temperature difference is higher here because surface is warmer, therefore this flux will be higher. But once again, this flux dominates in the first few millimeters to first few centimeters in the atmosphere. And then the question arises, how is heat distributed to higher levels of the atmosphere? Because, of course, higher levels of the atmosphere are also warmer during noon hour than during the morning hour. To describe that, I will now erase this part associated with sun rays, and we will look into further transfer of this heat. And the further transfer of this heat goes through convection. So please check my video on convection. Convection is a process by which warmer air parcels or volumes of air are being lifted to higher levels of the atmosphere, and then consequently colder air is sinking down. How does this happen? Let's look, it's enough to look actually just one case. Let's say this case over here. Now, in this case, let us say that the adjacent region that was characterized by different type of surface, maybe water, maybe forest, whatnot, ended up being a little bit colder than this part of the surface over here, indicated by the thickness of these red lines. If that is the case, it is clear that the air over here will be warmer than the air above the adjacent surfaces. And that means we will have convection, which means this warmer and lighter air parcel will start moving up. And that results in the transfer of heat, because warm air is going up, transfer of heat from very close to the surface to higher levels of the atmosphere. Now, what do I mean by higher levels of the atmosphere? Well, sometimes this air parcel can only go up to 20-30 meters, sometimes 500 meters, sometimes 1 kilometer, sometimes entire depth of the troposphere, which you know from my previous videos is about 11 kilometers. Most of the time, these what we call thermals go up to approximately 1 kilometer, and that region is called atmospheric boundary layer. But sometimes they go all the way through the troposphere to the top of the troposphere, and in that case we can get deep thunderstorm clouds. At any rate, this is how convection brings heat to higher levels of the atmosphere. And of course, then we have some relatively colder air sinking down. And this is how the mixing of colder and warmer air happens in the atmosphere through convection. Now, from my video on convection, you will also kindly remember that there are two types of convections. This, what I depicted here, is known as free convection. Free convection happens only because lighter and less dense air is rising in the environment of relatively colder and more dense air. In other words, it is not associated with any wind or obstacles on the surface. We also have the so-called forced convection. If this is the same surface, and now we examine this situation in the presence of winds. Winds are increasing their speed with the height, and that results in turbulence, tumbling of air if you want. There is a lot of turbulence over here, and clearly if we now have warm surface, maybe here is warmer than here, and we will have this conduction flux in first few millimeters, then this heat is transferred to higher regions of the atmosphere through this turbulent motion. And this turbulent motion also brings colder air from higher regions of the atmosphere down to the surface, and that's how surface mixes heat that it gained from the surface. This is known as forced convection. And forced convection, remember from my video on the forced convection, can happen like this, where we have what we call shear in the wind. Winds are changing either speed or direction with height, causing turbulence. It can also happen if we have some obstacle over here, and now this obstacle abrupts smooth flow field, causing again turbulence. It can happen if this obstacle is not building like I indicated here, but much bigger mountain. And remember, it can also happen, namely forced convection, if we have two air masses, one light or warm relative to another one that is dense and cold, and if they collide, then the light air is forced to go above heavy and cold air. These are called atmospheric fronts, and that also causes forced convection. It is also very important to understand that forced convection, as you can see also here, is much better at distributing heat vertically than the free convection. Which means if we want to sketch temperature profile in only first few meters of the atmosphere. So here is height in meters. So we go 0, 1 meter, 2 meters, 3 meters. And here is temperature. How is temperature profile going to look like if we only have free convection, no winds? And how is temperature profile going to look like if we have forced convection? Well, in the case of free convection, it might look like this. In other words, we will have very steep temperature gradient with the height, or surface will be much warmer than 2-3 meters above the surface, because, as I said, this mechanism is not as efficient as transferring heat vertically as this mechanism. So how is the situation going to be in the case of forced convection? Well, perhaps something like this. So the surface will be somewhat colder because the mixing is so good that it kind of makes temperature profile almost independent of height, but not quite. Temperature still tends to decrease with height. So this is forced convection and full line is free convection. Now let us examine the evolution of daytime temperature using radiation budget at the surface. We shall start by considering temperature variation over a 24-hour period. If on the y-axis we have temperature and on the x-axis we have time, we start from 00, midnight, and then we have sunrise at 6, then we have local noon, then we have 6 p.m., and then we have 2400 hours or the midnight next day. Now, how would temperature vary in an idealized condition without wind throughout the day? Well, if we start with some value of temperature at midnight, let's say here, then the temperature will decrease until sunrise, and then it will start increasing, reaching maximum at around 4 p.m. local time, and then it will decrease, again reaching, let's say, the value that it had previous midnight. So this would be typical variation of temperature during a 24-hour period, and when I'm talking about temperature, I really mean temperature close to the surface, and we measure it at 2 meters above Earth's surface. How do we explain this? With putting focus on daytime hours. And clearly daytime hours are these, from sunset to sunrise. Well, to explain that using radiation balance, we plot here a graph that represents on the y-axis energy rate, or a rate at which energy is either absorbed at the surface or radiated by the surface. I will put just E, but as I said, keep in mind this is rate of energy absorption or emission. And here on the x-axis we have the same hours during this 24-hour period. From my video on radiation budget at the Earth's surface, we know that the solar radiation does not exist, of course, during the night hours, so it will be 0 during the night hours, but then during daytime it will have a parabolic shape like so. where the maximum intensity of energy absorption by the surface is at local noon. Now the next question is, this energy is absorbed by the Earth's surface, and the Earth's surface is radiating energy upwards in the long wavelength spectrum. Please check my videos on radiation to understand what is short wave energy, what is long wave energy in terms of radiation. And the rate at which surface is radiating energy might look something like this. Again, if we start with some value at midnight, then it is decreasing, and then it will increase, and then again it is decreasing, perhaps reaching the value that we had previous midnight. Now, we are interested particularly in this daytime period, as I indicated here. Keep in mind that whenever the blue curve is above red curve, that means surface is giving away more energy through long wave radiation than it is receiving through the short wave radiation. Here also the surface is giving away more energy through long wave radiation than receiving through short wave radiation. However, in this region where the red curve is above blue curve, we have absorption of solar radiation or gaining of energy through short wave solar radiation dominating over the loss of energy through terrestrial long wave radiation. So in other words, we can see that in this period the surface will warm, whereas in this period of blue arrows the surface will start cool down. Now you can see therefore that the minimum temperature will be at sunrise. At sunrise, why at sunrise? Because the sun is still not shining, so there is no gain of heat through absorption of solar radiation, but yet the energy is lost through this long wave radiation, and the maximum loss accumulated over whole night happens just before sunrise. And that results in minimum temperature at around 5-6 a.m. in the morning. That's when the night is coldest. Now the next question is, why is maximum temperature around, maybe I didn't depict this, here should be peak. Why is maximum temperature, T max, at around 1600? Well, and not at sunset. The reason is, you see, maximum intensity of the absorption of solar radiation is at solar noon. But if even after noon, the solar radiation absorption dominates the loss of energy through the long wave emission from the surface, and this accumulates over hours until 4 p.m., resulting in maximum temperature being at 4 p.m. In other words, you can see that after 4 p.m. approximately, the blue line is above red line, means surface is now losing more energy than gaining energy, and therefore temperature starts dropping, as you can see clearly. Until this local hour of 4 p.m., the surface is gaining more energy through absorption of short-wave solar radiation than losing through the radiation of long-wave terrestrial radiation. And that is clearly depicted here. And now you can understand this part of the curve very well, because as the absorption of solar radiation is increasing throughout the day, this temperature curve is increasing, and then once the emission overpowers absorption, temperature starts going down. Now let us look at daytime temperature analysis through the equation of energy budget. This is very simple. We will look into our famous equation that Q star is equal QH plus QE plus QG. And of course, I will explain what these are, although I discussed this in great details on my energy balance video. Q star is net radiation. Which can be positive or negative. QH is sensible heat flux. QE is latent heat flux associated with phase changes of water. And QG is ground heat flux. What do we mean by this ground heat flux? Well, if this is the surface of the Earth and solar radiation is absorbed, that means this Q star, then this absorbed solar radiation, let's indicate it like this, can be used to conduct heat to deeper layers of the ground. That's this term. It can be used to evaporate water, so a particle of water that was perhaps liquid or ice now goes into the atmosphere, becoming water vapor. That is this term. Or it can be used to heat the atmosphere through conduction that I discussed 2 slides ago, and that is this term. Which of these terms results in the change of temperature at the surface? This one. Therefore, the name sensible heat flux. It is heat that our body, us, can actually feel. So, if we want very high temperature in the atmosphere, then this net radiation, that in that case has to be positive, needs to be distributed in such a way that pretty much everything goes into sensible heat flux and very little goes into these other 2 heat fluxes. So we could also therefore say how warm can the surface and therefore air above the surface become? Well, I cannot tell you exactly the value, but I can tell you the warmest surface is the surface that minimizes latent heat and minimizes ground heat flux. And that would be very dry surface characterized with very poor conductivity. And that would be, for example, loosely packed sand, like certain sand beaches or deserts. Deserts are very, very dry. This is therefore very small. And loosely packed sand is not very good at conducting heat to deeper layers, so this is also small. Which means if the radiation is absorbed, this term is positive. Everything goes into increasing temperature of the air, and therefore it is so warm above beaches and the deserts because this term dominates. Of course, if we go to, for example, forest area or agricultural fields, then we have plants and trees and other type of vegetation. And vegetation is moist, and we have therefore evaporation from both moist soil as well as moist plants called evapotranspiration, which means this term increases, thereby decreasing this term. So in other words, it is not as warm as over the surfaces which dominate this term. And of course, the surface that dominates in terms of latent heat is big bodies of water, such as oceans, seas, rivers, lakes. Over there, we have huge amount of latent heat. In other words, this solar radiation that is absorbed by water is used to a large extent to evaporate water, which does not increase the temperature of the water. And that is why it is much nicer to be on hot sunny days next to big bodies of water than deep inland. because when you are next to big bodies of water, this radiation is used to evaporate that water and thereby not to increase the temperature of the surface and then the temperature of the air. Whereas if you are deep inland, there is no water, so most of this net radiation is used to increase the temperature of the air. This was a video, perhaps a long video, but I hope you enjoyed it, about daytime temperature variation. In the next video, we are going to discuss nighttime temperature variations. Please make sure to like and subscribe, share this video, let's grow the channel, place a comment underneath the video, apparently it helps a lot. And until next video, goodbye.